Good morning, everyone. We'll wait just a couple of minutes and we'll see how this goes. Again, today I'm having a little difficulty with the internet being a little slow to respond and some flickering. And well, with that said, I guess let's get started. Shannon will be taking care of our comments in that, and I will also look over there and see if I can answer any questions. I'd like to welcome you to the fourth installment of the Came from Outer Space. I'm Craig Whitford. I'm a volunteer meteorite collections coordinator at Abrams Planetarium on the campus of Michigan State University. And today's subject is meteorites from the asteroid for Vesta. And I've got a little 3D model of Vesta here as it would be flying around the solar system in the asteroid belt. And we'll talk a little bit about Vesta too. Well, although meteorites are extremely rare, thousands of them have been found on the surface of the Earth, from the desert areas to Antarctica. A few of the meteorites found on Earth have been attributed to specific solar system bodies. A small number, less than 0.25% of all meteorites found on Earth, have been carefully studied and attributed to be from the Moon or Mars. A few have been studied thoroughly enough to be attributed to the asteroid Vesta. Some researchers believe that an amazing 5 to 6% of all meteorites found on Earth originate from Vesta. Oops. And Vesta just fell from the sky. Now, researchers have learned a lot about the chemistry, mineralogy, and isotopic composition of rocks from the Moon by studying specimens brought back to Earth by NASA's lunar missions. The characteristics of rocks on Mars have been determined through analysis done by rovers. We're asked those questions a lot. So how do scientists actually know? Well, we had the rocks that were returned by the Apollo missions from the Moon in the late 1960s and early 1970s. And then Mars, we've sent a large number of spacecraft, both orbiting and rovers, to search the planet and to gather all of this data. So Vesta is no different. Between all the scans and the Dawn mission, which mapped Vesta and the asteroid series as well, have confirmed that meteorites that have landed here on Earth have come from either Vesta itself or similar asteroids that have the same compositional characteristics as Vesta. While orbiting Vesta, NASA's Dawn spacecraft scanned the surface of the asteroid, collecting data about its chemical and mineralogical composition. The information has confirmed, as I said, that what's known as the HED meteorites, which is a subgroup of stony achondrite meteorites, are actually pieces of Vesta. Now remember, in stony meteorites, we have what are called chondrules, those tiny little dust particles that make up that planetary body. Well, in achondrites, we don't have chondrules or chondrites from that, and we'll get into the reason here soon. Well, how Vesta got its name? It was discovered at Bremen, Germany on March 29, 1807 by Heinrich Wilhelm Olbers, who had previously discovered the asteroid Pallas. For Vesta's discoverer, and that means that is the fourth asteroid that was discovered for Vesta, gave the honor of naming the new asteroid to German mathematician Carl Friedrich Gauss, who had computed Vesta's orbit. Gauss named it Vesta after the goddess of hearth and household in Roman mythology. Vesta is the second most massive body in the main asteroid belt, accounting for almost 9%. Imagine that, 9% of the total mass of all asteroids. Only the dwarf planet Ceres is more massive in that region of rocky debris between Mars and Jupiter, where the asteroid belt lies. NASA's Dawn spacecraft circled Vesta from July 16, 2011 until September 5, 2012, when it departed its journey and headed towards Ceres for another mapping exercise. Now, if you ever have some free time, and a lot of us have no place else to go right now, there's a wonderful diary online that tracks Dawn's mission to the planet, around the planet, and then on to Ceres. And you can just look that up on the internet. And I would just search NASA's Dawn mission. The giant asteroid is almost spherical, and it's nearly classified as a dwarf planet. Unlike most known asteroids, Vesta is separated into crust, mantle, and core, which is known as a differentiated body, much like our Earth is separated. We have a core, we have a mantle, and a crust. Understanding why this is so was one of the objectives of the Dawn mission. The answer turned out to be that Vesta formed early, within 1 to 2 million years of the birth of the solar system. Short-lived radioactive material that was incorporated into the bodies that formed during this epoch heated them to the point where, in cases like Vesta, the objects melted, allowing the denser materials to sink to the asteroid's core, and the lower density materials to rise to the surface. Vesta has one of the largest brightness ranges observed on any rocky body in our solar system. The bright materials appear to be native rocks, while the dark material is believed to have been deposited by other asteroids crashing into Vesta. Scientists on the Dawn team estimate that between 300 dark asteroids with diameters ranging from 1 to 10 kilometers, so 0.6 to 6 miles, hit Vesta during the last 3.5 billion years. This would have been enough to wrap Vesta in a blanket of material, bury it basically, 3 to 7 feet thick. An extensive system of troughs encircles Vesta's equatorial ring, and you can see those in images better online of the asteroid. The largest is bigger than the Grand Canyon. So that's fairly extensive, where it just has carved out all of that material down several layers. Vesta appears to be the source of the HED meteorites, which stand for Howardite, Eucrite, and Diogenite groups of meteorites that have been found on Earth. They help scientists understand the lunar cataclysm, when a repositioning of the gas giant planets billions of years ago destabilized the orbits of the asteroids in the early asteroid belt and triggered a solar system-wide bombardment. They also provide clues to Vesta's evolution. Vesta, it's believed to have lost about 1% of its mass less than 1 billion years ago in a massive collision responsible for the Ray Cilia crater, which is about 310 miles or 500 kilometers wide. Some 95% of the asteroid's mean diameter is what that equates to. The Vesta family of asteroids is probably debris from this collision. And so that's why I say that the meteorites that have fallen have either come directly from Vesta or Vestan-type asteroids, other ones. The impact is thought to have launched about 1% of the volume of Vesta as ejecta, exposing multiple layers of crust in the walls of the crater and possibly exposing some of the olivine mantle as well. The impact is thought to have been the source of the HED meteorites, again found on Earth, and about 5% of those that are discovered. So what I'd like to share with you now is I'll show you a couple of images here. This would be a sketch of Vesta. Its shape, which is rather odd, and you can see this mountainous region here where it had been bombarded and carved right out. If you look closer, you could see the where the meteorites have come from, the diogenites, part of the HED, the eucrites, or lava flows, which would be basaltic, and where the olivine and that are, and crossing these layers. So if you were to take a cross section of the asteroid, it would look something like this. This is what's been proposed right there. And you can see the different layer formations just as on Earth. And those sketches in that have come from this book, which was on my book list earlier. If you'd like to take a read, this is Rocks from Space by O. Richard Norton. An excellent beginning reference there, and for even in-depth study. Now, the HED meteorites are achondrites, as I had mentioned, so they don't have chondrules in them, but they are a stony meteorite. They're similar to terrestrial igneous rocks. They are thought to have originated from Vesta. The three groups are howardites, eucrites, and diogenites, HED. These differ in mineral composition and texture, which are determined by their history while still part of the crust of Vesta. Now I'm going to be sharing with you some meteorite samples to give you an idea as to what each of these meteorites look like. And the first is howardites. And they're kind of among my favorite. They're kind of like a garbage dump of things that make up each of those stones. And so they have some interesting characteristics. Howardites are known as regolith brachias, made up of eucrite, diogenite, and some carbonaceous chondrites. So, like I said, a garbage pile, a mishmash of material. They're believed to have formed on the surface of Vesta from impact ejecta, which was buried by later impact debris. Remember, we talked about that 3 to 7 feet layer of debris, and lithified. There are no known terrestrial equivalents to this type of rock. So from Earth, there isn't anything that matches it. Now remember, a brachia is a rock consisting of angular fragments cemented together. And you will see that. And so why don't we take a look at some of these, and if you could see that, all those different little fragments that are in there. And what is cool about this specimen is we also have the outer surface of it, which if you look, you can see just pieces adhered to the back there on that. And in collecting meteorites, we're going to do a segment on collecting meteorites here in a couple of weeks, but having an end cut, which is what this is, gives you the best of both worlds. It gives you what the original exterior looked like, and it shows you clearly what the interior looks like with all those fragments, the breccia that it is, and all the material it contains. And that was Northwest Africa 2696, again found in the Sahara. Here's another one of 2696, and this is a small slice that has a piece of the crust still on it, and you can see all of the makeup of that. Maybe if I get really close here, you can really make it out. So, kind of cool. These were actually found in 2003, 2004 in the desert. And this one is still waiting completion of its classification. So in the meteorite world, we call it a provisional number that's been assigned to it when it was submitted. Another howardite is Northwest Africa 2698. And I like to give you the names just in case you ever want to look them up and find them. 2698 has a lot of fragments into it. The white material you're seeing there is a north site, which is something we also see on the moon and on Earth. And you can see the fracture line through the center of that one. This one was found in 2004 in Morocco. There was only a single stone. That was a complete slice, and the stone weighed only 134 grams. It is paired, and we talked about that last time when we discussed the moon. It is paired with a couple of other meteorites as well. Oops. There we go. Another howardite is Northwest Africa 6393. And you can see it has some of the fusion crust still on it, right there on that edge. And you could see the makeup of that piece. And let's flip it over here. And see if the camera will focus in on that. Right there. And you can see the edge too, which shows the fusion crust that's on that. Again, this is another provisional meteorite that hasn't had the entire classification done yet. It was discovered in 2005. Prior to those finds coming from the desert, there wasn't much in the way of variety of meteorites to be found, because we typically waited for them to fall, or they were being found in the North American desert and Antarctica and that. But such a wide variety of meteorites have been found, from lunars to Martians to the HEDs to typical meteorites on the Sahara Desert. And as we also discussed, they're a little bit easier to find because the rocks generally are dark. Now, the last howardite I'm going to share with you is Northwest Africa 12227. This was found just a couple of years ago in Algeria. 1,780 grams was the original stone, and this one probably shows the breccia the best in there. And you can also see some little flecks, and those are nickel in there. This is a complete slice from this rock, and it's actually rather beautiful. And again, there's only one specimen on this. You could kind of get a gauge of the size. This is almost 5 grams, so not 20% of an ounce, basically, of that meteorite. So those are the howardites. Now, HED, so we're moving on to eucrites. Basaltic eucrites are rocks from the crust of Vesta that are composed mainly of calcium-poor pyroxene, pigeonite, and calcium-rich plagioclase. Eucrites have similar compositions to basaltic eucrites. However, they have oriented crystals and are thought to be intrusive rocks crystallized in shallow plutons within Vesta's crust. Now, a pluton is a body of intrusive igneous rock. So, some of the other terms that we used were culminate, which is an igneous rock formed by gravitational settling of particles in magma. Pyroxene, which is any of a large class of rock-forming silicate minerals, generally containing calcium, magnesium, and iron, and typically occurring as prismatic crystals. And plagioclase is a form of feldspar, common in igneous rocks and typically white would be the feldspar. So let's take a look at some of the eucrites. And we will start with a beauty. which was found in 1999 in Oman. The total known weight was around 50 pounds that was located, and this is a eucrite. Little bit different structure and texture than the howardite. Okay, you could see the shock veins that run through it, which you might call cracks. This is a full slice of this, and you can see those bright white areas and the other fragments that make it up. This is, again, a full slice, and as you can see, there's some fusion crust left on the edge. Look at how thin that is. And over the years, they have become quite expert in cutting these thinner and thinner. It's not uncommon to see meteorite slices now in the 0.5 millimeter range, where in the past, historically in the past, they would be several millimeters thick, and you'd get a nice thick sample. Keeping with this one, which is Dhofar 007, so kind of like 007. There you go. This is the same, a little bit thicker slice. Shows you that melt vein that's in there that runs through there, and those angular fragments that make it up, and you can see where this side has been polished. There's still some fusion crust on it, and it's just a beautiful meteorite. This one's fairly common, actually, if you can call any meteorite common. So the next one that we're going to look at is Northwest Africa 2690. Was found in Morocco in 2004. About 33 pounds of material was found, which is quite a bit. So there are many pieces. This one's paired, oddly enough, I think with a howardite, perhaps. Which, remember, some of these meteorites are a amalgamation of other materials from the surface of Vesta. And this is a nice large slice so that you can see all the different things. And you can always hop online if you want to learn more about the makeup, what's involved, as far as its geochemistry and things like that. All that information is online. And I'm just trying to give you an introduction to this. So this is Northwest Africa 6577. This was found in Morocco in 2011. And when I say Morocco, a lot of times these were bought in Morocco but found elsewhere. But the nomads in that don't necessarily release the GPS coordinates of where they do these finds as they find them. So it's a little more difficult. They may have been purchased by a dealer and in Morocco, and so that's why they're given the location of Morocco. 770 grams in a single specimen were found, and again, it's just a nice, beautiful, representative example. This is a polymycete breccia composed of lithic and mineral fragments derived mostly from basaltic and eucritic lithologies, plus some sparse diagenite orthopyroxene is what makes that up. So quite a mouthful, and that's why I say go online if you want to learn a whole lot more of the detail in that. Let's see, this should be a nice little end cut again, which are always my favorites. You can see that is the exterior of the stone, and if we turn it around, you could see the polished face, the cut face of it, and all the little tiny minerals in that make it up. But having the best of both worlds and being able to see the exterior helps in learning to identify, and sometimes by sight you can make a rough guess as to what type of meteorite it might be. And so there's that one. Here's a nice one. This one was found in the Western Sahara. It's Northwest Africa, 7496. This is a partial end cut. And if you look at this, you can see it's got a domed face to it, which meant this one was probably oriented when it entered the atmosphere, and because it wasn't a perfect orientation in that, and when they decided to go ahead and have a cut, but you can really get an idea of the exterior here, and also of the glossy fusion crust that's on it, that you could see there. So this is a fairly nice specimen that even has a good write-up online. Northwest Africa, 7496. So have a look. Northwest Africa 8647 is another eucrite. This is another end cut. Best of both worlds. You could see the polished cut face of it. And you could see the melt, which is the black area there. That was liquefied at some point. And the angular fragments that are left, dark. And if I flip it over, you could see the fusion crust with some chips in the surface which expose the matrix. So that's 8647. And my last eucrite, just amazing variety in each one of these stones. Some of them are paired, and I've told you about that when it does happen, because different individuals submit stones at different times, and they're assigned a number, and then afterwards they have to go through and kind of figure out what it's paired with, what has the same chemical composition. So here is the last of the eucrite specimens I have to show you today. Again, it's an end cut, so it shows you the exterior surface with some fusion crust, and shows you a nice view of the interior of the rock. So when you get all of these together and lined up, it's actually pretty impressive. Well, the last of the HEDs are the diogenites. And diogenites are believed to have crystallized in deep plutons. Remember, that's an intrusive body of igneous rock within Vesta's crust. They have a much coarser texture than eucrites and are composed mainly of magnesium-rich orthopyroxene, plagioclase, and olivine. So, and the last diogenite I'm going to show you has an interesting name, which I'm sure you'll all enjoy. But starting with our first diogenite is from Western Australia. Wow, something that isn't Northwest Africa, which is just great. And among the diogenites, there are several that have been seen to fall. This is not one of them, but this is Camel Donga. And this was found on the Nullarbor Plain in Western Australia. It has this beautiful, rich patina on it that is just amazing. And this one is just about 100% covered, if not 100% covered in fusion crust. And so it's a beautiful stone. Again, found in January of 1984, about 55 pounds, made up of a lot of specimens. This one is fairly available if you're interested in looking at starting a collection. This one is just over an ounce, so kind of cool. And it's an absolutely stunning exterior. A fall of a diogenite was observed in 1924 in Johnstown, Colorado. And about 89 pounds was the total take on this one. This is really tiny, but if I can get it out of the glare there, you could see it up there, and it has tiny olivine crystals in it as part of the diagonite. This is a fairly scarce meteorite from that standpoint, and it's just really, really attractive. And it's a fall. It's an observed fall, not a find. The next one is back to Northwest Africa. NWA 4473. This was found in 2006 in Morocco again. About 15 pounds worth of material. This again is a part slice or cut, an end cut. And you could see I'm getting a lot of flickering of my screen going on here. So you can see the makeup of that and its cut surfaces. And here is a complete slice of that. It's green and black and white and quite an attractive specimen of a diagonite. Sticking with Northwest Africa, seems to be a theme. This is NWA 7464, found in 2012 in Morocco. You can see some fusion crust on it right there, and you can see where the chips have taken it. About 5 pounds and 81 pieces was discovered. And again, they're digging these all out of the sand, okay? If they find one in an area, they just keep searching and searching until they get most of it. So there's a specimen of 7464. A real beauty from the diagonites, and talking about olivine. Specimens of this particular one, this is Northwest Africa 7831. It was found in 2013. Excuse me. Specimens are composed of yellow-green crystalline. You can see those crystals there sparkle a little bit. Crystalline, almost entirely translucent, including grains of nickel-free metal, trilite, chromite, anorthite, etc. In these. And this is an individual fragment. We call it a fragment. Broken off probably a larger piece. This is really friable. If I were to rub this, I could get crystals off. They would flake right off of it. And so to give you an idea of its translucency, here is a complete slice. And if I take a flashlight and hold it up there, you could see the material that it's composed of. And again, these are in, tiny crystalline sheets, basically, that you could flake right off of there if you wanted to. But such a beautiful example of a diagonite. If you were looking for one for beginning a collection of those meteorites from Vesta, this would be one that would be on my list. And that is Northwest Africa 7831. 7831. So the final specimen I'm going to share with you, as I mentioned at the top, is a meteorite that was seen to fall in Tunisia in 1931. Officially, it says around 26 pounds of material was found, but a lot more has been found since this was actually classified. I have 2 specimens of it. And, oh, I haven't given you the name yet, huh? Oh, okay, well, I guess I should probably do that. But this is just an incredible meteorite. This is green and black and glossy, and rarely are these seen with fusion crust on them. And the name of this one is Tatooine. Tatooine. If that sounds familiar to you, it is because of the Star Trek or the Star Wars connection. Oh, I'm going to be in a lot of hot water over that. But the Star Wars connection with the planet Tatooine was inspired by the place where this meteorite actually fell. And these meteorites above 10 grams are pretty scarce to come by. Most generally, all we see are smaller fragments in the 5-gram or less range. But you can really see that, and that is just a stunning example. For a while, we had some of these available at the planetarium in our gift shop there. And once we're back open again, I'm sure we'll have more of these available for you if you're interested in adding one of those inexpensively to your collection with the connection that it does have. So I see that somebody says that the rock that I was holding at that time is pretty. Yeah, it is. It's a pretty nice one. I'm kind of partial to the meteorites anyways, but so with that, I hope you've enjoyed your visit to the planet Vesta. You've gotten to see some of the rocks that make up that planet that have survived in space for millions and millions of years, only to land on this planet and for us to really enjoy studying them. So next week, we're going to take a look at some Mars rocks, and Mars has an interesting history, and in just the last few years, some great science has been accomplished with some of the meteorites that have been discovered in Northwest Africa, of course. And we'll talk about where some of the meteorites are found from Mars, what they contain, and how they assist us in what our search is for life on the planet. So with that, I'd like you to be sure to check out all of the activities at Abrams Planetarium Facebook page. We have Spartan Young Astronomers coming up this Saturday at 10 a.m., and that'll be a live event. We have the Science of Star Wars, whoa, coming up on Monday, May 4th at 7 p.m. That you're not going to want to miss. And you've even seen a meteorite that has an association with Star Wars. There's Celestial Story Time, and you can catch that a couple of days a week. There are sky calendar updates. Have a look at those and what's happening in the sky, and much more. And since we're closed during this time period, I know that Shannon will probably put up a link for donations. We encourage you to make a donation, and we certainly look forward to the time that we reopen, and we look forward to seeing you all then. Until next week, keep your eye on the sky, stay safe, stay home, and take care. Have a great day.